Let's talk about a very special series called a geometric series. Geometric series is really one of the foundational series that we need to work with in chapter 11. And the first thing I want to point out is that in general, we can't actually find what the series sums to. Okay, so I'm going to even highlight that because I think it's important. In general, we can't actually find the sum of the series. All we can really do usually is we can only determine whether the series converges or diverges. So when we do 11.3, 11.4, 11.5, 11.6, we're really only going to concern ourselves with whether the series converges or diverges. However, there are two cases in this course where we can calculate what the sum of the series S is. And those two series are, well, the first one is the geometric series. That's what this particular video concerns itself with. The second type is something called the telescoping series. And we cover that in a subsequent video. But of these two, the geometric series is by far more important. Okay, so let me describe what a geometric series is for you. So if I were to write out what the terms of a geometric series looks like, it looks like this. The first term will be called A. The second term, to get the second term, we take A and we multiply by R. To get the third term, we take A and we multiply R again by R again. So you'd get AR squared. The fourth term would be AR cubed, and so on and so forth. So if we were to write out what the general term looks like, the general term is going to be A times R to the n minus 1. And that goes on forever. So remember, this is the nth term, an. So one thing you'll notice is that we have a n minus 1 power here. And that's because the very first term doesn't get multiplied by r. But the way you get from one term to the next is you multiply by r. And when we add all these guys up, that makes this a geometric series. So A is going to be our first term. And R is what we call the common ratio. So that's how you get from one term to the next, is by multiplying by the common ratio. And as I said at the beginning of this video, this is one of the few series where we can actually calculate the sum. So what we're going to need to do is we're going to need to work with the nth partial sums. So let me write the nth partial sum, Sn, and that's going to be equal to A plus A times R plus A times R squared plus, and we keep going, and then the last will be A times R to the n minus 1. Okay. And then what we're going to do is we're going to do a clever trick here. We're going to take this series, we're going to multiply it by the number R. So we're going to take R times Sn like this. And when I do that, what am I going to get? Well, I'm going to get A times R would be the first term. But when I write it down, I'm going to write it in the second slot here. So I'm going to put AR like this, and then AR squared like that. That's the second term. And then so on and so forth. So the second to last term would be AR to the n minus 1, but the actual last term is going to be AR to the n. Okay, and that's the results that you get when you take Sn and you multiply by R. And all I did was I took that series and just kind of shifted it to the right a little bit so the ARs line up and the AR squareds line up like this. Okay. And then what we want to do next is we want to subtract these two series that I just wrote there. So let me draw a line like so. That's not exactly straight, but I won't worry about that. And then when I subtract these two series, what am I going to get? Well, on the left-hand side, we're going to get Sn minus R times Sn. And then what do I get on the right-hand side? Well, A minus nothing is A. But when you subtract AR from AR, you get 0. AR squared from AR squared, you get 0. The second to last term is also going to be 0. And only this guy is going to survive. So I'm going to have plus 0 plus 0 plus blah, blah, blah plus 0. And only the very last term is going to be minus AR to the n, like so. All right. And then what I'm going to do is I am going to factor. So I factor a Sn out on the left-hand side. I get a 1 minus R. On the right-hand side, what did I get? I had A minus A times R to the n power. All right. And then I can divide both sides by 1 minus R. I get the nth partial sum is going to be equal to A times 1 minus R to the nth power, all divided by 1 minus R. Okay, so this is our nth partial sum. So I'm going to highlight this. This is our nth partial sum. Now I'll even put a little comment. The nth partial sum. Great. Now, in our last video, we saw that a series is going to converge as long as its sequence of partial sums converges, right? So I have this sequence of partial sums that looks like this, and I want to take the limit to see if it converges. So let me slide this up a bit over here, like so. So we know that the sum of the series S is going to be equal to the limit as n goes to infinity of the sequence of partial sums Sn. Okay, and we want to calculate what that is. So let's do that. So the limit as n goes to infinity of Sn, that's going to be equal to the limit as n goes to infinity of A times 1 minus R to the n divided by 1 minus R. We can really split this up into two series, right? If you sort of distributed the A and the ARN minus 1 like that, we can see that this series could split into the limit as n goes to infinity of A over 1 minus R minus the limit as n goes to infinity of A R to the n power divided by 1 minus R, like so. Okay, now I want us to pay special attention to this term right here, this Rn term. And I've run out of room, so let me continue down below over here. What we know from studying exponential functions is, R to the n is an exponential function, right? We had looked at this example in the previous section. So just as a quick reminder, if R is bigger than 1, the graph looks like this. If R is between 0 and 1, the exponential function looks like this. So my point is that when R is bigger than 1, the series is going to diverge. And when R is between 0 and 1, where really absolute value of R is less than 1, then this converges. So we had seen that last time. And what does that converge to? That's going to go to 0. All right. So what I'm trying to say is that this whole term on the end here, it's either going to be 0 or it's going to make our whole series diverge, the whole thing diverge. Because once one piece diverges, this whole thing is going to diverge. Okay? So to summarize, if the absolute value of r is less than 1, the series converges. If the absolute value of r is greater than or equal to 1, the series diverges. And we know what the series is going to converge to. So in particular, the series S is going to be equal to the limit of the, as n goes to infinity, of the nth partial sums. That's just going to be that a over 1 minus r piece that we had found earlier here, right? Because this second piece is either going to go to 0 or it's going to diverge and explode to infinity. So really, this shows that, all right, we know how to find the sum of a geometric series. So let's take a look at an example. Let's take a look at an example 5 over here. When I look at example 5, I need to first see that we have a geometric series. Okay, so I look at the first term, the first term is a, that's equal to 5. And when I think, how do I go from one term to the next term? Well, when I look at this, I can multiply 5 by 2/3. And then how do I get from the second term to the third term? Well, if I take the second term and multiply by 2/3, I get the third term. And let me just check one more time. If I take the third term, I multiply by 2/3, I get the fourth term. So when I look at that, that tells me that my r is equal to 2/3, and we have a geometric series. So now I can find the sum. The sum S is just going to be a over 1 minus r. That's equal to 5 over 1 minus 2/3, which is equal to 5 over 1/3, or 15. So this concludes our video on the geometric series, but we use the geometric series throughout the rest of this chapter. So please make sure you understand these ideas, and we will do more examples in class together. All right, everyone, take care.